Hello everyone. This is about section 7.4 in our textbook, and as I had mentioned in my July 6 post, the difference between section 7.3 and 7.4 is that in section 7.3 we are estimating a population mean when we know the population standard deviation. And section 7.4, in that section we estimate a population mean when the population standard deviation is not known. So what we do in that case, we use a t-distribution, and instead of the standard deviation of the population, we use the sample standard deviation, and there'll be a few other changes. And I will explain all of this by using some examples I'd like to show you in detail how to work some of the exercises. And I think that'll give you a lot of insight how we treat section 7.4. So let's look at example or exercise number 9 about earthquake depths. So they're referring to data set 16 in Appendix B, which is irrelevant here. It lists the depth in kilometers of a sample of 50 earthquakes. Those 50 depths have a mean of 9.808 kilometers and a standard deviation of 5.013 kilometers. Construct a 98% confidence interval estimate of the mean of all such depths. So here's the relevant information. The population mean is 9,808. We use it as the sample mean as well. And the sample standard deviation is 5,013 kilometers. N is equal to 50. The confidence level is 98%, so alpha is 2%, and alpha divided by 2 would be 0.01 or 1%. Now the margin of error is equal to t sub alpha divided by 2 times s, the standard deviation of the sample, divided by the square root of n. So what is t sub alpha divided by 2? Well, it's t sub 0.01 times s, and s was 5,013, and n is equal to 50. And now we just need to find out what t sub 0.1 is for degree of freedom. Since n is 50, the degree of freedom is 49. So we look at the t table, the t distribution, and since we don't have 49, we use 50. And for 1%, there would be, where are we here? 2.403. For 1%, here's 50, and here's 1%. So 2.403 is our t sub 0.1. So 2.043 times this expression of 5,013 divided by the square root of 50. And that is then equal to 1,703.6 or 1,704 if you round it up. And so again, our confidence interval is mu minus e, the margin of error. And again, that's equal to sample mean. And so then that gives us for the confidence interval 8,104.4, and the true population mean is in between these two values, the x bar or the mu plus the margin of error, and that's equal to 11,512. So to go over the process one more time, we're using the sample statistics here. The sample mean of 9,808 kilometers, a sample standard deviation of 5,013 kilometers, sample size n of 50, which gives us a degree of freedom of 49, and with a confidence level of 98%. That means alpha is equal to 0.02, and then alpha divided by 2 is 0.01. So we need to look up t sub 0.01, and again in the table we find for a degree of freedom 49, but again since that's not in the table, we use the next highest one for 50. That is 2.043 times s, the sample standard deviation, divided by the square root of 50. And so here's our margin of error of 1,703.6 or 1,704 kilometers. So when we add that to the sample mean and subtract it from the sample mean, we have our confidence interval of 8,104 kilometers and 11,512 kilometers. The next example is about the amounts of mercury in parts per million, or ppm, found in tuna sushi, sampled at different stores in New York City. And that, excuse me, that of course is relevant because mercury is toxic in the human body. So here are the data. The sample mean is equal to 0.719 parts per million, and the sample standard deviation is equal to 0.366 parts per million, and the confidence level is 90%. Confidence level is 90%. So it means that alpha divided by 2 is equal to 5%, or 0.5, and n is equal to 7. So we have degrees of freedom equal to 6. When we look at the t-distribution table, and for degrees of freedom 6, and for alpha divided by 2 being 0.05, our t sub alpha divided by 2 is 1.943. So our margin of error E is t sub alpha divided by 2 times s divided by the square root of n. So that means our margin of error is 1.943, our t sub alpha divided by 2, times 0.366, our sample standard deviation, divided by the square root of 7, and that's equal to 0.2688 parts per million. And so our confidence interval for this true population mean would be x bar, the sample mean, minus the margin of error, and x bar plus the margin of error. And by performing these calculations with a sample mean of 0.719 and the margin of error is 0.2688, our confidence interval is between 0.45 parts per million ppm, less than the true population mean, less than 0.99 parts per million. So here's the confidence interval for exercise number 10. Next, we're going to look at CEO compensation. And so here we have the compensation for 5 chief executive officers. And so 11, so the sample information is that the sample mean is $12,898. And the sample standard deviation is equal to $7,719. n is equal to 5, so our degrees of freedom is equal to 4. And our confidence level is 95%. So alpha is equal to 5%, or 0.05, and then alpha divided by 2 is equal to 0.025. So for our t sub alpha divided by 2, our t sub alpha 0.025, for degrees of freedom of 4 at alpha at 0.025, when we look at the table, 0.025, and here's degrees of freedom is 4, and here's 0.025 is 2.776. So that's our t sub alpha divided by 2. So 2.776. Therefore, our margin of error is equal to t sub alpha divided by 2 times s divided by the square root of n. So that becomes then 2.776 times 719, our standard deviation, divided by the square root of 5, and that is equal to 9,583. So our margin of error, the sample mean minus the margin of error, less than the true population mean, less than the sample mean plus the margin of error, would give us 3,315, less than the population mean, less than 22,481. So that's our confidence interval. And when I use technology just to check the answers, slightly different, it came out to 3,314, less than the population mean, less than 22,483. So I'm giving you lots of examples so that you know how this works when we don't have the population standard deviation and we use a t-distribution to compute the population mean when the population standard deviation is not known.